Hello guys, in this video we are going to discuss a problem that is faced with Hough transform, and further we will also give a solution to this problem. So let's get started. So previously in Hough transform we have seen that Hough transform is basically used for edge linking. So if suppose I have kept my image on this coordinate axis. So this is the x-axis and this is the y-axis, and I have kept the image over here, and there are two edges that are detected over here. So what are these edges? These are basically the pixel values. So there are these pixels spread out in the image, and suppose there is this edge and this edge that is detected over here, but then edge is not a point, edge is a line, so we need to link this basically. So that is what is done with the Hough transform. So we have seen how the Hough transform works. It basically converts from the xy plane. So basically if we want to join these 2 points, we have the equation that is y is equal to, suppose, ax plus b, where a is the slope of the line is a, and b is nothing but the y-intercept. So what we do in Hough transform is basically convert this space from xy to the parametric space that is known as the AB space. So what we do is we take this over here, so we get basically y minus ax is equal to b. So this I can also write b is equal to minus ax plus y. So now if you see, if I go into a parametric space where here at the x-axis I have a and at the y-axis I have b, here there is b in the y-axis, so every point in the xy plane changes to a line in the AB plane. Similarly, every point here, this point over here in the xy plane will change into a line in the AB plane, and then what we suppose this point corresponds to this line. Suppose I am just giving an example, and this point corresponds to, say, this line. So then the point of intersection in the AB plane then gives you this line that is joining the 2 points. So we have discussed all these points, that this is easy for a computer. So this is that we have seen in the Hough transform. Let us see what is the problem with this. Let us consider that the 2 points are like this. That is this is the xy plane. Here we have the image, and the 2 points are vertical to each other. So suppose the coordinate of this point is, say, 2 comma 1. So this is 2, this is 1, so the point is 2 comma 1, and the coordinate of this point will be 2 comma 2. Let us consider. Let us see what happens when we convert it to the parametric space. So we have this equation that is over here. So we have b is equal to minus ax plus y. So let us put the first point over here. So in place of x I will put 2, and in place of y I will put 1. So we get b is equal to minus 2a plus 1. So this is my first equation in the parametric space, the AB space. The next equation that will come is with this point, so 2 comma 2. So the next equation will be b is equal to minus 2a plus 2. So this will be my second equation. Let us plot these two graphs. Let us get a rough plot of these two graphs. So so this is a, this is b. So here you can see, suppose when a is equal to 0, we get b is equal to 1. So basically when a is equal to 0, we get b is equal to 1. Suppose this is 1. Okay. Now next, suppose a is equal to 1. When a is equal to 1, when you put a is equal to 1, you get b is equal to minus 2 plus 1. So minus 2 plus 1 is minus 1. So when a is equal to 1, say this is 1, you get b is equal to minus 1. So if this is 1, this will be minus 1. So this is the point. So basically you get a line like this. Oops. So this is the point. So this is the line that we get. Next, suppose we want to plot this line. So when a is equal to 0, we get b is equal to 2. So when a is equal to 0, we get b is equal to 2. So this is the point. And say when a is equal to 1, you get b is equal to 2 minus 2, that is 0. So you get b is equal to 0. When a is equal to 1, you get b is equal to 0. So this is the line that you get. So here there is this problem that these two lines are parallel to each other. You can see the slopes of both the lines are same, but the y-intercepts are different. So these two lines will never meet each other. These two lines will never meet each other. So if they never meet each other, I will never get a point, a single point. So I will never be able to get a line that will join these 2 points. But actually in reality, it is possible to join these 2 lines with a single line. But through Hough transform method, since these 2 lines are parallel, they will never intersect, and hence I will never get this line over here. So this is the problem that we face in Hough transform. So let us see what we can do with it. First, let us also see why is this problem coming. So what is the cause of the problem basically? So here you can see that the line over here has a slope of infinity, because this is a basically in signals and system you will see that this is a discontinuous line. You cannot say what is the y coordinate at this 2. I cannot say that it is 1, I cannot say it is 2. It is all these points actually. So it has a slope that is of infinity. So because it has a slope of infinity, and we are actually plotting nothing but the slope and the y-intercept over here. So because the slope is infinity, we are getting this problem. So this is because of this thing that we are facing this problem. Let's see how can we solve the problem that was faced earlier. So while doing this, in the first place, what we did was basically we transformed the xy plane, the xy coordinate plane, to the AB coordinate plane, where A was the slope and B was the y-intercept. So we saw that the problem was caused due to this, the slope. So the slope became infinity and the problems arised. So basically we need some other parameters. If we can convert this xy plane in some other parametric plane where those parameters do not tend to infinity at any point of time, at any with any orientation of the line, whether the line is vertical, whether it is horizontal, or any orientation of line, that parameter space should give proper finite values, then the problem will be solved. So then what we came up was is known as the normal form of a line. So let us see what is actually happening in this normal form. So what we basically do is, say consider this is the line. This is any line in the xy plane. So this is the xy plane and this is the line. So this is basically what we want. We don't have the line, we will have points. But what I am actually trying to do is, we have this equation y is equal to ax plus b, but since we have this problem with this slope and intercept, I am going to convert this line into something else, and then we will do the same procedure that we did earlier. So consider that this is the line that we have to actually find out. So the equation of the line will be y is equal to ax plus b as earlier. Now what we can do is, basically my aim is, if I have two parameters such that I will take a perpendicular from the origin to the line. So this distance, let me consider it as p, and the angle made by this perpendicular, let me consider is at theta. So here, now in my new form of equation, what I am going to do is, basically I am going to use this p, that is the distance from the origin when a perpendicular is drawn to the line, and an angle theta of that perpendicular. By this, so these will be my two parameters in the parametric plane. So now the parametric plane is no longer going to be a AB plane, but now it is going to be a theta p plane. So on the x-axis I'll have theta, and right, on the x-axis I'll have theta, and on the y-axis I'll have p. So this is going to be a theta p plane. And how can I convert this from this? Let us see what we can do. So basically, if this is theta, I can write that this is some alpha. Let this be some alpha, the slope of the line be some alpha. So here I can write y is equal to, a is nothing but the slope, so slope can be written as tan alpha x plus b. So this is what we can write, tan alpha x plus b, because this is the slope. So we know that the slope is nothing but tan theta, the angle made by the positive axis from the line. So we did this. Okay, now we can see that this line, that is the perpendicular drawn, and this line are actually perpendicular to each other, because we have made it like that they are perpendicular. And we have this this theorem that the slopes of perpendicular lines are basically -1. So tan theta into tan alpha will give me -1. So this is the famous theorem that when two lines are perpendicular, their slopes will be -1. The product of the slopes will be -1. So I can write tan alpha is nothing but -1 upon tan theta. That is what I can write. So here let us put this in this. So we get y is equal to -1 upon tan theta x plus b. So this is what we get. Next, what I'm going to do, I'm going to convert this tan theta. So I'll write I'll write tan is nothing but sine upon cos. So I'll get sine theta upon cos theta into x plus b. Next, let us multiply this sine theta throughout. So I'll get sine theta into y is equal to minus cos theta into x plus b into sine theta. That is what I'm going to get. I have multiplied by sine theta throughout. So let us take this cos theta over here. So I get cos theta x cos theta plus y sine theta is equal to b sine theta. So let me consider this b sine theta as some p. So let me just replace this b sine theta, because b is a constant, sine theta is a constant, so p is another constant. So let me replace this whole thing by p. So I get x cos theta plus y sine theta is equal to p. So this is nothing but the parametric equation, but in the normal form. So this is what is known as the normal form of a line. So we have this basically relation between x, y and theta and p, as we had this relation over here. We had b is equal to minus ax plus y. This was a simple relation, but since we faced that problem over there, so we then converted this line into another parametric space, where p is nothing but the distance from the origin when a perpendicular is made, and theta is nothing but the angle made by the perpendicular, that is theta. Okay, so now if we want to plot a line, say let me consider the same example. This was the problem creating agent over here, basically this vertical line. So let us put these equations over here and see what we get. These equations over here. So what I'm doing is I'm converting that line. So let me draw that line over here. So this is my xy, this is my xy coordinate axis, and what I'm going, so these were the points. I have 2 comma 1 and I have 2 comma 2. This is a point, this is 2, this is 1 and this is 2. So these are the 2 points that we have, and we need a line that should join here, join the 2 edges basically, using Hough transform. So let me put this equation, this value of x and y in this equation, as similar we used to do earlier also. So here I'll get 2 cos theta plus I'll get 1 sin theta is equal to p. So now this is what I need to plot in the p theta plane. Next, the other equation will be 2 comma 2. So I have 2 cos theta plus 2 sin theta is equal to p. So let us plot these equations. These are nothing but sinusoidal curves. So let us plot these equations. Let us see how they look, and let us see how they will give this answer that we need. So since these are curves that we are going to plot, so I am going to use Desmos. This is a free software that is available online to plot these two curves, and let's see what happens. So first let me give a label. So my x-axis is going to be theta. So the x-axis is theta and the y-axis is p. So that is what I have. So it is very easy. You just have to write p is equal to what equation. So my equation was 2 cos theta plus sine theta. So this is my first equation, so that is giving me a curve like this. My next equation was p is equal to 2 cos theta plus 2 sine theta. So now there is this problem that we are getting multiple what we call intersections. So we just need one intersection. So what we can do is basically we can restrict the value of theta. So let me just consider theta from minus pi by 2 to pi by 2, because I just want one single intersection point. I don't want to see others. So I'm restricting the value of theta from minus pi by 2 to pi by 2. So this is what we get. So we can see that there is only one point over here, this point, where it is intersecting. So here this point is nothing but 0 comma 2. 0 comma 2. So basically what we got is 0 comma 2. So this says that P is equal to 2 and theta is equal to 0. So our line, so we saw that if this is the xy plane, so this was the theta p plane, so the parametric plane. If this was suppose the xy plane, so the line should have a distance of 2 and sorry, theta is 0. I made a mistake over here. Theta is equal to 0. This is theta and this is p. So theta is equal to 0 means it is this, and p is equal to 2 means the distance from the origin to this line will be 2. So what we need is one line that is perpendicular to this. So we can see that this line that was earlier not possible using the Hough transform method that we used earlier is now very much possible using this method. So by this method you can basically take any value of xy, you can take any point and you can plot it, and then you see the intersection and you just take the theta value and the p value and it will give you your line. It will give you any line that you want. So this was basically the solution to the problem that we faced. Thank you so much for watching. Thank you so much.